Hello, this is a presentation on the paper Quantum Annealing for Single Image Super Resolution by Choong, Suryansh Kumar, and Luc van Gool of ETH Zürich. This paper is part of the CVPR 2023 New Trends in Image Restoration and Enhancement workshop. To preface this presentation, I would like to provide an overview of our work. Our work is an early exploration of applying quantum computing to the image enhancement task of single image super resolution. The reason for this exploration is the exceptional capabilities of adiabatic quantum computing to use quantum phenomena such as superposition, entanglement, and adiabatic evolution to solve combinatorial optimization problems with exponential speedup over classical computing. As such, in our approach, we cast the super resolution problem into one of combinatorial optimization, and in particular, we use a quadratic unconstrained binary optimization formulation for sparse coding. Having developed our approach, we evaluated it on popular super resolution datasets. Now, to more concretely define the problem of single image super resolution, or SISR, it is that of reconstructing a credible and visually adequate high-resolution image from its low-resolution representation. SISR finds applications in medical imaging, remote sensing, and scientific research, to name but a few domains. Currently, commonplace among the state-of-the-art in super resolution are deep neural network models. The SwinIR is an example of a current top-performing SISR model, with its architecture being based on sliding window transformers. Given the proven performance of deep neural networks in super resolution, our goal in this work is not to argue against this prevailing paradigm, but rather to undertake an early exploration of applying quantum computing to super resolution. We believe this to be a worthwhile exploration due to the exceptional capabilities of quantum computing to solve combinatorial optimization problems, and also in light of the high level of activity in quantum computing research, where in recent years, increasingly capable quantum processing units have been developed and made available, enabling their use on practical problems. We expect this trend to continue towards the future, where quantum computing will play an increasingly prominent role in machine learning. To provide more context, out of the two types of quantum computing available today, in this work, we focused on adiabatic quantum computing. In this type of quantum computing, hardware advancements have made it increasingly possible for it to be applied to solve practical computer vision problems in recent years. The fundamental problem that is solved by adiabatic quantum computing is the quadratic unconstrained binary optimization problem, or QUBO problem. In this problem, Z is a binary vector to be optimized with respect to the matrix Q containing quadratic coefficients determining the quadratic terms, and the vector B determining the linear terms. Once defined, the QUBO problem is embedded onto a physical lattice in a quantum processing unit, and then optimized by quantum annealing. Clearly, the QUBO problem is a highly specialized combinatorial optimization problem, and therefore, in order to solve super resolution using adiabatic quantum computing, it is necessary to find an appropriate formulation that casts super resolution into the QUBO form. For this, we refer to the work Image Super Resolution, a Sparse Representation of Raw Image Patches by Yang Jianchao and Ma Yi and colleagues from 2008. In the method of image super resolution via sparse representation, high resolution images are constructed patchwise, with each high resolution patch given by a sparse linear combination of raw image patches. This is encapsulated in the equation x equals d sub h times alpha, where X is the linearized high-resolution image patch, D sub H is the learned dictionary, and since alpha is a vector containing sparse coefficients, the atoms of D sub H thus consist of the aforementioned raw image patches. Sparse coefficients alpha are found by solving a L1 optimization problem based on a paired dictionary D sub L. To be clear, D sub L and D sub H form a coupled dictionary pair. With corresponding atoms, the atoms of D sub L are obtained from low-resolution image patches, whereas the atoms of D sub H are obtained from high-resolution image patch counterparts. This L1 optimization problem occurs in low-resolution image space, and the sparse solution alpha obtained is then transferred into high-resolution image space for use in inference. In our approach, we make the modification of casting the aforementioned L1 optimization into binary form via a discretization step involving a hyperparameter mu. Following this discretization step, we find that the L1 optimization objective has a QBO form with clear expressions for Q and B obtained from terms in the L1 optimization objective. With this appropriate QBO formulation of binary sparse coding, image resolution by sparse representation can now be implemented on QPUs. That is to say, a form of super resolution can now be solved using quantum computers. To train our algorithms, we followed the approach of Yangjian Chao and colleagues, 2008. We evaluated our algorithms on the Lena image and set 5. We developed 3 algorithms in total, namely lasso regression, which carries out conventional sparse coding, classical annealing, which solves super resolution by simulated annealing on a conventional computer, and quantum annealing. All of our algorithms carry out 3 times upsampling. Following evaluations, overall, we found that classical annealing and quantum annealing achieve the same accuracy. We found that annealing-based methods outperformed bicubic interpolation and conventional sparse coding on the full Lena image and set 5. However, as expected, we found that the performance of sparse coding approaches nevertheless falls short of state-of-the-art deep neural networks such as SwinIR. In summary, through our work, we carried out an initial demonstration of applying quantum computing to super resolution with encouraging results. We obtained evidence of superior sparse coding performance of classical and quantum annealing over conventional sparse coding in the super resolution context. Beyond PSNR results, due to the nature of our algorithm, allowing for a quick succession of quantum measurements to obtain many samples, our algorithm design enables a way to do fast, robust prediction and uncertainty estimation. While the speed of our algorithm does not yet match that of conventional sparse coding due to the cloud-based computing model and limited quantum computing resources, we nevertheless identified a way to increase the speed of our hybrid classical quantum algorithm by reducing classical computational loads and transferring them to quantum processing units. With that, I conclude my presentation, and I thank you for your attention.